Hello everyone. What I am reporting today is dual-channel speech enhancement using neural network adaptive beamforming. My name is Jiang. First of all, let me introduce what speech enhancement is and the types of speech enhancement. Speech enhancement algorithm is an important technology to process speech in noisy environments to improve speech quality and intelligibility. Types of noise suppression are mainly divided into single-channel speech enhancement and multi-channel speech enhancement. Another is stationary noise and non-stationary noise. Our papers propose a dual-channel speech enhancement method. The datasets come from the MSSSD dataset provided by DNS Challenge. The 180 hours DNS Challenge noise set includes 150 classes and 65,000 noise clips, and the clean speech set includes over 500 hours of clips from 2,150 speakers. We use image method to make the dual-channel dataset. The target source is in the direction of 0 degree, and the interference sources are randomly distributed between 0 degree and to 90 degree. Well, in the formula, NCK is the noise and SK multiply HK is our target source. And HK is room implies response. Our goal is to remove the noise NCK and keep clean speech SCK. We use image method to make the dual-channel dataset, as is shown in the figure. In addition, training dataset is 200 hours and validate set is 20 hours, and the test set is 5 hours. NABDTM block diagram is shown in the figure. The input is time domain, and the output is also time domain information. So this is an end-to-end noise suppression model. Also, the input information is dual channel, and the output information is single channel. From the picture, the L means the length of frames. The detail of the model will introduce next. From the picture, we can see the output of TCN will multiply with the output of encoder, and then decode the output, we will get the enhanced waveform. We use the loss function SR-SDR to update our model weight. Next is the detailed structure of our neural network model, which is mainly composed of two parts. The first part uses 3 LSTM layers and 2 linear layers to estimate the beamforming filter coefficient of each channel. Then XE will multiply with HE, XI will multiply with HI, and use this formula to communicate the output of NAB. We know the tau C is the relative delay of each channel, but we use this formula, the second formula, to communicate the output of NAB. While we drop out the tau C in because the coefficient of HCK is updated by the loss function of target speech and the predicted speech. So tau C is implicitly expressed by HCK. The output NAB is used as the input of the Denoise-Tensnet model for further noise reduction process. In Denoise-Tensnet, the structure of TCN is shown in the figure. We repeat one Demosin convolution block with dilated convolution factor D for 3 times, and the TCN we can see in Denoise-Tensnet is very important. The Denoise-Tensnet includes one Demosin convolution and near normal, and convolution, and then is TCN. The output of TCN will decode to get the predicted speech. The weight of our model is updated by SR-SDR loss function. Calculate SR-SDR from the signal as caret predicted by the model and clean speech as in SR-SDR. The numerator is target and the denominator is noise. Obviously, the bigger the SDR, the better. So we want to minimize the noise part to get the beta. Next is the display of result part. We compare each model through PSQ and STR. Our model is better than other models under different SNR, such as MMSC, DNN, CRN, and MFMVDR. For example, in 5 dB, our proposed method is better than MFMVDR. The same to PSQ is also the result. Next, the performance of the proposed method when interference source at different directions where STR and PSQ are the average of below 5 dB, 0 dB, and 5 dB. We can see, nevertheless, the average PSQ and STR of the noisy have been greatly improved. This is the noisy STR, and this is the PSQ, noisy PSQ. And this is noisy MOS. From the table, we can see it has been a greater improved, which means the NABDTM model is not greatly affected by the amount of interference source. Therefore, the proposed model is more adapted to complex things. Spectral analysis. Next is the display of the finally, let me see. Okay. We show the changes of spectral before and after noise suppressing. The red rectangle is in this part shows the frequency spectrums of stationary noise, and this is non-stationary noise. We can see in hamster spectrums, this part is removed, and this part is also removed. So, regardless whether it is stationary or non-stationary noise, the model can also remove the noise. In addition, the distortion of enhanced speech is very small from the white rectangle. It shows, compared with enhanced spectrum and clean spectrum, we can know in high frequency it has a slight distortion, and in low frequency, the distortion is smaller. Conclusion. In this study, we proposed a neural network adaptive beamforming and developed a cover translate struct for dual channel speech noise reduction. The cover translate was originally tasked of processing a time-domain speech separation, but we produced a denoise mask instead to achieve single-channel speech denoise. The NAB take multiple input to perform beamforming in processing noise. The end. Thanks for your watching.